My name is Thomas Hasenpusch. I'm working as a measurement engineer with in the radio monitoring station Munich of the Federal Network Agency in Germany. And as a measurement engineer, I have a lot. I'm dealing a lot with all kinds of RF measurements of all services, especially interference investigations. And today I will present two topics that are related to my work. The first one is measurements of digital signals with spectrum analyzers. Although this may sound pretty basic for experienced engineers, I experience that in many cases there are still questions and doubts as to how to correctly measure a digital modulated signal with a spectrum analyzer. So first a few things about the spectrum analyzers themselves. We have two different types of spectrum analyzers. One is the classical sweeping analyzer that scans the desired frequency range with a narrow filter. And then we have FFT analyzers. They capture the time signal for a certain time and then they calculate the spectrum mathematically. Sweeping analyzer in theory sweeps a filter through the desired frequency range that is adjusted as the span. So if we have a signal and we take a filter, we sweep it in time through this signal, and then we get after the filter is swept, we get the display on the screen. In practice, it is realized a bit different because it is difficult to realize tunable filters of various bandwidths. It is cheaper to have them fixed frequency filters, and we can get the same result if we keep the filter at a fixed frequency and then we sweep the signal through the filter. The result is the same, but this is how it's done in practice. And from this presentation, one thing we already noticed is that it takes a certain time to do this sweep. So by the time we see the presentation of the left end of the span, the signal may have already changed. The presentation of the signal on this end of the spectrum is at a later time than at that time of the spectrum. And because digital signals tend to change very fast, usually the spectrum analyzer, the sweeping spectrum analyzer, is too slow to present a real-time, to give a real-time presentation of the true spectrum. We always have the time component in this. Oh, actually, I wanted to skip this sheet because the time is a critical factor in the presentation. Actually, you have it on the DVD that you get, but these are the different components of a sweeping analyzer that we don't want to get too much in detail about at this point. Unfortunately, I tend to have not the latest version of this presentation on the stick. But those are the different stages where we can adjust the different parameters of the spectrum analyzer. The resolution bandwidth, however, is a critical parameter. It describes the ability of the analyzer to separate two different signals. In this example, the two signals are spaced 30 kilohertz, and of course you can see that with a 3 kilohertz bandwidth we can separate them clearly, but using a 30 kilohertz bandwidth you can just see a 3 dB dip to tell us that there's two signals and not one. However, it is not always able to separate two signals that are spaced as far as the resolution bandwidth. This only works if they have the same amplitude. This example has the signal with the same frequency spacing, only the amplitude of the right one is lower, and in that case, if we use the 30 kilohertz resolution bandwidth, we cannot see that it is two different signals. It looks as if it is one signal. So in any case, the smaller the bandwidth, the resolution bandwidth, the better the frequency resolution. But also it takes longer to perform the sweep. And we have to find a compromise, and the optimum setting is the span divided by the display pixels. So if we have an analyzer with 500 display points from here to here, and we want, for example, to set a 500 kilohertz span, then the optimum resolution bandwidth would be 1 kilohertz. So that one resolution bandwidth equals the bandwidth of one pixel on the screen. This is the optimum setting for the maximum frequency resolution. If we narrow the bandwidth more, we only get longer sweep times, but not better resolution. Another critical thing is the envelope detector, but this is also a sheet that I wanted to skip. Actually, I think this version of PowerPoint does not recognize the hidden sheets. I have marked some sheets hidden, so it doesn't seem to display them in any case. Anyway, when we decode or demodulate the RF signal, we get the so-called video signal that shows only the amplitude changes that are due to the modulation. And this red line signal is then fed to the detector, and it measures, usually the analyzer measures much faster than it can display, which means that we have multiple measurement results behind each display pixel. And the detector determines which of the measurement values are displayed. So if we have a modulated signal, an amplitude modulated signal, the analyzer samples at that speed, meaning in this example we would have 12 samples with different amplitudes, and depending on the sweep time and the resolution of the screen of the analyzer, this may be two different pixels later on. So this means that we have 6 samples behind each display pixel. The question now is which of the 6 samples is actually displayed, and that is determined by the detector we use. If we use the peak detector, the highest pixel is displayed, which is this in that case, and in this second case it will be that pixel. If we use the average detector, then the average of all 6 pixels is calculated in voltage, and here also, and that value or this value is then displayed. If we use the RMS detector, all 6 pixels are averaged in power, which is maybe different than average of voltage, and that value is displayed. And then some analyzers also have a so-called sample detector, and the sample detector randomly picks the first pixel. So that is displayed here, and this pixel is selected in that pixel. So we need to understand how these analyzers work in order to see how the detectors can be used. Now for the FFT analyzer principles, Fourier has developed a mathematics that can transform a time signal into a sum of discrete unmodulated sine waves. Now if we have in this example, we have a couple of sine waves that are unmodulated, and they have different amplitudes and different frequencies. If we add all these sine waves pixel by pixel, we get the resulting wave that in this case looks nearly rectangular. But you can construct any time signal out of the sum of sine waves. And the theory says that we can also regain the sine waves in amplitude, frequency, and phase by applying the Fourier transform. And this is what the FFT analyzer does. This is the signal we feed to the antenna, and that is the display we expect from the analyzer. The formulas allow the calculation of the spectrum in any case, but it requires a large amount of calculations. And the fast Fourier transform greatly reduces the calculations. They have a few restrictions, but these restrictions can usually be accepted in the RF measurement theory. In any case, the time signal is first captured or acquired for a certain time, digitized and stored in memory, and then the spectrum is calculated from that stored time. So the block diagram of the analyzer would look something like this. First, the RF signal is down converted into a baseband, and then it is fed through a low-pass filter and digitized, and the result is then stored in memory. And the DSP then calculates the spectrum out of the stored samples. From this diagram, you can also see one restriction or one issue with the FFT, and that is that we usually get no seamless record of our spectrum. Usually we have blind times, because first we have a time where we acquire the signal from the antenna, then this block is processed, and after the processing time we get the resulting spectrum. And then the next block is acquired, processed, and displayed. And during the processing times, we are blind on the input of the analyzer, because anything that happens during that time we cannot record. And in many cases, this processing time can be much longer than the acquisition time, so that we actually only get snapshots of the signal and no seamless acquisition. Now, some analyzers overcome this problem by applying two different processing lanes and switch the antenna signal from one to the other. So while the first lane acquires, the second can do the processing, and then they switch tasks. That may overcome this problem, but of course it doubles the costs of the hardware. And when we come to pulsed signals, and digital signals are often pulsed, then there's another issue with FFT, namely it depends on the time when we actually acquire the signal. Usually the FFT is fast enough to show the spectrum of even the shortest pulses. But if this is a pulsed signal and we acquire during that time, it is obvious that we don't get anything on the spectrum display, because the transmitter is off. So we see only the noise. If we do the acquiring exactly during the pulse, we may see an unmodulated carrier. Only if we do the acquisition and capture the transition between on and off, then we see the typical pulse spectrum of the signal. So it depends where we place our FFT window, our acquisition window, and it depends on the time that we acquire what spectrum we see. Now, for the levels of digital signals, we have different levels that are important. The peak level is the maximum possible level over a long time, and that applies when we want to assess the interference potential of a signal. And the RMS value is valid in all other cases. It is the average power over a long time. And that applies nearly in all cases when we, as the monitoring service, want to measure a signal. When we want to check whether a reception is possible, when we want to check whether the station works according to the license, and if we want to measure coverage. In all cases, we need the RMS value. But if the signal is pulsed, this RMS value is replaced by the average burst value. And the average burst value is the same as the RMS value, but only measured during the pulse. So we spare the pauses when we do the measurement. And that is, of course, much more complicated to measure. So it applies like RMS, but it applies to bursted signals or to pulsed signals. So if we have a pulse here, a burst, then this average level is the interesting level that we want to know, not the average including the pauses. So before we want to do level measurements, we need to know the bandwidth of the signal, because that affects the setting of our analyzer in the level measurement. So the first step usually is to measure the bandwidth of a signal. And since digital signals usually have a constant bandwidth, with very few exceptions, it is relatively easy to measure. The most important bandwidth is the 99% bandwidth. This is the bandwidth in which 99% of all transmitted energy lies. So if the digital, or if a signal is displayed in a certain span, the analyzer counts all the energy that it sees and sets that as 100% reference. So it is important to show the analyzer everything down to the noise. So we cannot make the span as narrow as this, and if we make it too wide so that next neighbor channels are visible, then the measurement is also invalid. We need to adjust it in a way like this, and that is then judged as 100%. And then the analyzer starts to integrate to the left and to the right of the signal, and that until it reaches 0.5% of the previously stored 100%. And it sets markers here and there. And in between these two markers is the 99% bandwidth. So this is how the analyzers function work, and that's called the occupied bandwidth. And we can use this, we can measure it by using a narrow resolution bandwidth. Max-hold function is allowed because the signal is noise-like in most cases. The digital signals are noise-like. Therefore, max-hold is allowed. And then we use the occupied bandwidth function that is implemented in almost all modern spectrum analyzers. So this works for pulsed and non-pulsed signals. Now that we know the bandwidth, we can go to measuring the level. With a sweeping analyzer, to measure the peak level, we set the span either to the signal bandwidth rider or zero span. That is not so important. Important is the resolution bandwidth that we use, and that must be at least as wide as the signal bandwidth. We cannot measure any levels with a narrow resolution bandwidth. We need to set the resolution bandwidth as wide as the signal. The detector, of course, is peak, and the trace may be max hold. And then we read the highest level with a marker. Pretty straightforward. If we want to measure the RMS level, we use the span also to be at least the signal bandwidth. We use the narrow resolution bandwidth. As mentioned before, the optimum is span divided by display pixels. And then we use the RMS or sample detector. If the analyzer doesn't have RMS, we can use sample. We have to use clear white as the trace mode, and then we use the channel power measurement function. This is also a function that is implemented in almost all analyzers. If the reading is unstable, we can increase the sweep time. That will make the reading more stable. But we can never use max hold with this, because the max hold function will destroy the averaging that is done by the RMS detector. Now the more complicated thing is the average burst level. We can measure that only in the time domain. So we set the analyzer to 0 span. The resolution bandwidth must be at least the signal bandwidth. The detector is RMS or sample. We have to use clear white, and we can trigger the burst so that the sweep only starts at the burst start time. The sweep time must be at least as high as the burst time, and then we use a function that is built into some analyzers that is called time domain power measurement. So we get a display like this. You can see the pulse here, and this analyzer has a possibility to set start and stop lines here, and this result here is the resulting RMS power only measured from here to here. If we cannot set the red lines, then we can increase or decrease the sweep time so that the span that the sweep time is equal to the burst time, and we see only the burst. And then we can do the power measurement during that time. But if the analyzer does not have this power measurement method, we cannot measure the average burst level with that analyzer. We cannot use the channel power measurement function on bursted signals. The average level is not so important, but it can be measured with these parameters. Sorry, I wanted not to skip this too fast, but average is also can be measured in 0 span, but with average detector. So if we have an FFT analyzer and we want to measure the signal, the peak level, we set the capture bandwidth, of course, to be at least the signal bandwidth to capture the whole signal. And we do a time domain analysis and select the shortest possible acquisition time. So we acquire as fast as the instrument allows. And then we do a max hold function over multiple acquisitions. Alternatively, we can also use an amplitude versus time display. This pretty much is the same as the 0 span for sweeping analyzers, and we use that together with long analysis times and read the highest value. The RMS level is set with is also acquiring whole signal, but it uses the channel power function that is also built into these instruments. And together with long acquisition times or averaging, we get a stable display. If it's unstable, we can increase acquisition time or number of averages. The average burst level, again, we capture the whole signal, we trigger the analysis on the burst start and use the channel power function, but we have to set the acquisition time equal to the burst time. In this example, this is an LTE burst. Well, you can see this is the captured signal, and this is only part of that is the analysis time, and that is the channel power measurement during that time only. So this can be done only with FFT analyzers. Okay, this I wanted to skip actually under low S to N ratios, correction values, but this is also a blind sheet. Yeah, actually, this concludes this short, very short presentation. Actually, a few recommended literature can be found in the Spectrum Monitoring Handbook, Chapter 4.3, where this topic is also described. Thanks very much so far.